right? Slope of the line tangent to a curve. Well, if you up the dimension, you know, the line is a it's a reference to a two-dimensional figure. If we're referencing a three-dimensional figure, we would want to have something that exists primarily in the three-dimensional plane, the three-dimensional coordinate system. Right. So coming up with the tangent plane, and there's I have a whole activity on how these formulas came to be, but for now we're just kind of working with the formulas. So find the equation of a tangent plane normal and normal line to the surface, z equals x squared y squared plus 1 for this equation. I'm sorry, for this set of values. So we have the equation here. It's written out for us. It's nice. You see those little subscripts for the f's. Those are our partial derivatives. So we're evaluating the function, then we're finding partials, then we're going from there. So what I would first want to do is figure out what f sub x would be. In this case, we're differentiating the x squared, holding everything else constant. So 2xy squared. The 1 goes to 0. Then the first order partial with respect to y. So there we're holding everything except for the y constant. We're taking the derivative with respect to y. Everything else is either a constant multiple or a constant itself. So derivative of y squared is 2y. So we're looking at 2x squared y. So what we'll do is we'll focus on each of these coordinates one at a time. But all we're doing is popping these values in to that model. So it's really not that bad. Just takes a little doing, right? So let's focus on 1, 1. So that's an a value and a b value. All right. So the z equation, equation of tangent plane, f of 1, 1 plus f sub x of 1, 1 times x minus a. So in this case, x minus 1. And then the same thing just with the y's. All right. So plus f sub y 1, 1 times y minus 1. Resize. So now we just start plugging and chugging away. All right, if I plug a 1 in for x and 1 in for y in the original function, I'm getting 1 squared times 1 squared plus 1. So 1 times 1 is 1, plus 1 is 2. Plus the first order partial, make that a little thicker. First order partial with respect to x, that's this guy over here. Popping in a 1 and a 1. We do the same thing for the first order partial with respect to y. So if I plug in a 1, I'm going to get a 2 again. 2 times x minus 1 plus another 2 times y minus 1. And then we just clean it up, right? Because we're accustomed to our tangent planes, our planes having a particular form. Typically don't look like this. So we could leave it as a function of two variables, but we could also distribute it out and get it into the standard form for a plane. All right, so this would cancel with one of these. So we'd be looking at 2x plus 2y. I'd bring the z over, so minus z. And then I'd add the 2 the other way, so it's more familiar in terms of the equation of a plane. All right. So then, doing it for 1, 0 isn't really going to amount to a whole heck of a lot. In terms of work, you're just going to do a lot of the same stuff again. just with ones and zeros. In fact, let me shrink this down. If we do it at 1, 0, plugging in a 1 for x and a 0 for y. All right, so that's going to zero out the first part of my z equation. So I'm just going to get a 1 plus plugging in a 1, 0. Well, if 0 takes any part of in the partials, if 0 is either x or y, the whole thing's zeroing out. All right, so it actually turns out that we're going to get 0 times x minus 1 plus 0 times y minus 0, which all cleans up nicely to just a line z equals 1. All right, so that's not too bad. For 0, 1, z equals, plugging in a 0, 1 for x and y still gives a 1. But then, like I said before, plugging in a 0 for either x or y in the first order partial is going to give a 0, so everything else is going to collapse away. So you just stop right there. And then just move on to the 0, 0 case. Z equals, plug in a 0 for x, 0 for y, you still get a 1, everything else cancels away. Right? So it actually turned out that the only part of this that we had to do any work for was the first part. Everything else ended up being kind of nice. Okay, so I'll just kind of pop this over here. Now it said also to do the normal line. Normal line, slightly different, but it has the same ingredients for the most part. Yeah, so for the normal line, it's parametric. So x is equal to, I just realized I'm supposed to do this for each one of them. I don't really want to do it for each one of them, and neither do you, I don't think. So I'll just do it for one of them. We'll do it for 1, 1. So plugging in a 1 for a, the 1 plus my first order partial, we discovered that way back when as being equal to 2, so 1 plus 2t. Y is going to be equal to 1 also plus 2t. And z, evaluating the function, gave us a 2, so 2 minus t. So that would be the normal line. It's normal to the plane. I guess I could do it for the other ones too. 1, 0. We got all the values, so might as well, right? So x would be equal to 1. But we knew that plugging in any 0 in our partials was going to cause it to zero out. So it's just x equals 1. All right. Y equals, that y value is equal to 0. And the slope there would also be equal to 0. And so z is going to be whatever the z value was, which we determined was 1, minus t. Zero, 1. It's going to give us pretty much the same thing, except the x's and y's will be swapped. So x equals 0, y equals 1, z equals 1 minus t. And then for 0, 0, x equals 0, y equals 0, and z equals 1 minus t. So it really wasn't that bad. It's just a fair amount of number crunching. Okay. So I'll pop a star on number 2. And next class, we'll talk about the chain rule. All right, so that's where we're going to leave it for tonight. Stop the recording. I'll get that